Okay, let's do another problem from Chapter 6. A horizontally directed force of 40 newtons is used to pull a box a distance of 2.5 meters across a tabletop. How much work is done by the 40 newton force? Well, if we drew a picture, we have a box. Then we have some force pulling it this way of 40 newtons. And it's going to go a distance of 2.5 meters. We are asking about work, so what is the work done? We know the force, we know the distance, it's 2.5 meters. Well, if we look at our equations for work is equal to the force times the distance, and its unit is joules. So if we take a newton times a meter, we'll get a joule. So let's just plug in our numbers here and we can solve this problem. So take 40 newtons times 2.5 meters. That's equal to our work. I'll let you plug in the numbers. Remember, your answer should be in joules. Okay, let's try another problem from Chapter 6. A force of 60 newtons used to push a chair across a room does 300 joules of work. How far does the chair move in the process? So we have a chair. This is my chair. We have a force of 60 newtons. We know the work done, so I just got to write this, just make a list here. Work is 300 joules. Let me rewrite the work. Right, so we're asking what is the distance that this chair has gone to do that much work. So we're looking for distance. Well, we can use the equation that we just used in the problem prior to this. Work equals force times distance. Force times distance. I want to rearrange the equation to solve for distance, not work. So right now it's solved for work, but I want to get d by itself. So I'm going to divide both sides by the force. F divided by F is 1. So now we have the work divided by the force, F, is equal to the distance. And a joule divided by a newton is a meter. So that's the unit we should have is meters. Alright, so you're just going to plug in 300 joules and divide by 60 newtons. That will be your distance, and make sure your answer is in meters. Okay. Let's try one more from Chapter 6. A string with a constant of K of 40 newtons per meter is stretched a distance of 20 centimeters from its original unstretched position. What is the increase in potential energy of the spring? So here's our spring. This is going to be bad. Okay, that's our spring. It's attached to something here. We're going to then stretch it out. This is like the normal position. We're going to stretch it out 20 centimeters. So we're going to stretch. So we pulled it out an additional 20 centimeters from its resting position. So let's write down the things we know. We know the K constant of the spring. It's different for every spring. It's 40 newtons per meter. We know the distance that it's stretched is 20 centimeters, but we want to be in meters. Notice, let me highlight this. Our K is in, our constant's in meters, Newton per meter. So let's make this into meters. So take 20 centimeters. For every 100 centimeters, I have 1 meter. So take 20 divided by 100. So our distance is 0.2 meters. Okay, what is the increase in potential energy? So what's the potential energy by stretching it out there? So do we have an equation for that? Yeah. You look, we have an equation for springs. Potential energy in a spring is equal to half of a stretched spring. We're looking at the additional potential energy is half of K times the distance squared. I think what your book uses is X here, but it's just saying this stretched out distance. So your book might have an X. It's the same thing. It's the distance that it's been stretched. Okay, so let's plug in the numbers here. We have 1/2 times K of 40. That's Newton per meter. Solving for the potential energy. And we're going to multiply it by d squared, so 0.20 meters. Alright, so I'm not going to do the math part. I'm not going to do 1/2 times the 40 times 0.2. You can do that. But I will look at the units here. We have Newton over meter times, oops, this is all squared, remember that, times a meter squared. So I'm just looking at the units. Potential energy is going to be measured in work, so we want this to equal work. Well, meter squared divided by meter is just meter, so Newton, get Newton times meter. A Newton times a meter is a joule. And so potential energy is measured in joules. That's what we want. So if you just write out do the math here, take 1/2 times 40 times 0.2 squared, do your 0.2 squared first. That answer, that number, is joules. Okay. Do we got time? Let's try